redshift 2? Was there simply, oops, tells me it's being recorded. All right. What was different at redshift 2? Was there simply more fuel for the star formation? Or was star formation somehow also more efficient? And to answer this, we need to actually observe this fuel. So stars form predominantly from cold molecular gas, and the main component of this is molecular hydrogen. Unfortunately, molecular hydrogen isn't actually observable in emission at the tens of Kelvin that are typical of the molecular interstellar medium. So instead, we rely on the emission from dust and from carbon monoxide. So dust being a catalyst for the formation of H2, and it's well mixed with the gas, and carbon monoxide, the second most abundant molecule in the ISM. So to convince you of the fact that dust and CO are indeed found in star-forming gas, here I'm showing two images of the Orion Nebula. And in the optical image on the left, you can see some recently formed stars, and you can see the dust that makes up the Horsehead Nebula. And the image on the right, you can see CO emission from these same regions. But we want to observe all of this dust and the CO emission from galaxies at redshift 2 in order to measure the total molecular gas content. And before we constrain the molecular gas masses of these galaxies with different observations, we need to check that they actually provide the same results. So thanks to ALMA, dust continuum observations have become a very time-efficient way of probing the molecular gas content of galaxies. But prior to about 2018, it was unclear whether these observations actually yielded the same molecular gas masses as observations of the typical or traditional tracer of molecular gas, the ground transition of CO. So theoretically, dust emission should be an effective molecular gas tracer at long wavelengths, so within the Rayleigh-Jeans regime. And in this regime, the emission is optically thin, so the observed flux density is directly proportional to the dust mass and the temperature of the emitting dust grains. So if you know the dust to gas ratio, or you have some good assumption on it, you can use this observed flux density to then measure molecular gas mass. And various studies have used this fact to calibrate dust emission as a molecular gas probe. So one calibration that's become very popular for high redshift galaxies is that of Scoville and his collaborators. So this calibration is based on this tight relationship between the CO1 to 0 line luminosity and the dust continuum luminosity at a rest frame wavelength of 850 micron. And so this calibration was performed using a sample of local star-forming galaxies, low redshift, ultraluminous infrared galaxies, and some lensed high redshift submillimeter bright galaxies. Okay, so this calibration and its use rely on a number of assumptions. So first, the single band continuum measurement, typically conducted with ALMA, has to be scaled to the rest frame 850 micron. And in this calibration, this is done by assuming a single modified black body with a power law and opacity and a mass-weighted dust temperature of 25 Kelvin. And also to actually get a molecular gas mass using this method. So this method assumes that the dust to gas ratio is the same for all of these galaxies, so around 1 to 100. And they use the same CO to gas mass conversion factor. Okay, so by 2018, the scaling method had been used to derive the gas masses of hundreds of high redshift galaxies, but it hadn't been tested on the same types of sources. So to test the use of dust continuum emission as a molecular gas tracer, we used a sample of 12 redshift 2 galaxies, which already had dust continuum observations with ALMA. And we spent a significant amount of VLA time then observing the CO1 to 0 emission. So these are all massive star-forming galaxies at redshift 2. So the aim here is to compare the CO and the dust-based molecular gas masses. And I'm about to show you two sets of data for the same sample, or 2 points for the same sample. So the blue points will show the gas masses estimated from single band measurements, so based on this single modified blackbody assumption, and the gray points are by fitting the full SED. So for this sample, we find that the gas masses derived from CO and dust continuum agree to within a factor of 2. And this factor of 2 can easily be accounted for by small variations in the dust temperature or gas to dust ratios. So this really implies that long wavelength continuum observations can be used as reliably as CO1 to 0 to estimate the molecular gas reservoirs of massive star-forming galaxies at redshift 2. And this is a relief because many studies have measured the molecular gas masses from continuum observations. And there's also been quite a few surveys over the last few years using CO emission to measure molecular gas masses. So these surveys have been trying to fill in this right panel here, which I'm about to show you. So this is the cosmic molecular gas density as a function of redshift. Okay, so thanks to the dust and CO surveys conducted over the last decade, we now have some constraints on the evolution of this cosmic molecular gas density. And you can see that it shows a similar trend to the star formation rate density. So it peaked around a redshift 2, and it's been declining to the present day. So this indicates that there must be some fundamental differences between galaxies today and at redshift 2. So one of these differences is the amount of molecular gas relative to the stellar mass. So in local galaxies, typically the stellar mass far exceeds the remaining reservoir of molecular gas. But typical star-forming galaxies at redshift 2 contain roughly equal amounts of stars and molecular gas. So this also implies that there must be something different about how gas and stars are distributed at redshift 2 compared to in the local universe.
I'm sorry, can I just interrupt for 1 second?
Sure.
Did you show us the previous slide and explain what the orange and the green contours are?
Sure. So the orange contours here show you data from, it's the A3 Cosmos survey, which is using calibration data from ALMA in order to probe the molecular gas content of galaxies at high redshift. And then this green contours here are all the galaxies in the FIBS sample. So this is a survey targeting CO emission, mostly CO3 to 2 emission with the NOEMA instrument and IRAM. So yeah, does that answer the question?
Yeah, and then the gray one is the local?
Yeah, so the gray one is a bunch of different local samples, so including Kingfish, X-cold gas, all smog. There's like a table of 10 different surveys that go into this. So this is basically a compilation of data from this study by in 2019.
What's weird is I thought I heard you say that the amount of molecular gas went down as a function of redshift, but you're saying it goes up as a function of redshift relative to the mass of stars. Is that right?
So it goes down as a function of redshift. So in the local universe, there is less molecular gas relative to the amount of stars. So local galaxies
down with decreasing redshift is what you're saying.
Yes.
Okay, I thought you meant down with increasing redshift. I'm fine now. Okay, thank you.
Okay, good. I hope that makes it clear for everyone else too. Yeah, so at redshift 2, galaxies typically contain roughly equal amounts of stars and molecular gas. So what we wanted to look at then is how stars, dust, and molecular gas are distributed at this peak epoch for star formation, and then make some comparisons to local galaxies. So in local galaxies, the emission from cold gas has been mapped down to scales of around 100 parsec, and we have even higher resolution observations of the stellar emission. So here I'm showing a really nice example of the CO2 to 1 emission and the stellar emission for the local galaxy NGC 628. So this is data obtained by the FANGS collaboration. And we can see that for these kinds of local galaxies, the gas in young stars are distributed in a spiral structure. And also by measuring the kinematics from the CO line emission, it's also become clear that in local galaxies, this molecular gas is distributed in a thin disk with velocity dispersions of around 10 kilometers a second. Okay, so how does this compare then to the distribution of stars and gas at redshift 2? So answering this was one of the key science goals for ALMA, which has now been in operation for almost a decade. So let's take a look at what has actually been observed so far with ALMA. So far, many of the galaxies that have been observed with ALMA have been submillimeter bright galaxies. So in other words, galaxies with very bright dust continuum emission and very large dust reservoirs. So here's an example of a redshift 2.1 submillimeter galaxy studied by Chen and collaborators. So in the left-hand panel, you can see the dust continuum in black compared to the CO emission in orange. And in the right, this dust continuum emission is overlaid on the rest frame optical emission from HST. So based on these observations, it looks like the dust emission is more compact than either this CO or the stellar emission. And other high redshift studies have been finding similar results. So here I'm going to show you a summary of the field at the beginning of the year. And in this left-hand panel, I'm comparing the half-light radii measured from dust continuum emission to the half-light radii of the 1.6 micron emission from HST imaging. And for all of these high redshift galaxies, so these include some compact main sequence galaxies, sub-millimeter bright galaxies, and dusty star-forming galaxies, which are basically the same thing. The dust emission looks 2 to 4 times as compact as the stellar emission. Okay, so what about for CO, which is obviously the main molecular gas tracer? So very few studies have been conducted with ALMA, constraining both the extent of the CO and the continuum emission. So for the few galaxies where this has been attempted, the dust emission also looks a lot more compact than the CO emission. So this would appear to call into question, again, the use of dust emission to trace the molecular gas. But I showed you before that the molecular gas masses derived from CO and dust continuum observations are equivalent for these kinds of massive star-forming galaxies. So why then is the dust emission more compact? Is this a sensitivity issue, or does it indicate that there's some difference in ISM properties as a function of radius? So for example, a radial decline in temperature or dust to gas ratio. And the other thing that's unclear is how this relates to the sample selection. So all these resolved ALMA studies that I was showing you targeted galaxies that are very bright and sub-millimeter wavelengths and also very compact. So it's unclear how representative these are. So to answer these questions, we really need matched resolution observations of dust and CO in more typical galaxies at redshift 2. So for this, we selected the 3 most extended galaxies from the Hubble Ultra Deep Field, for which we already had detections of the CO and the dust continuum emission. I can see someone popping up. Is there a question? No, okay. So these galaxies were detected as part of the aspect survey. So that's the ALMA spectroscopic survey of the Hubble Ultra Deep Field. And the nicknames of these 3 galaxies that I'll show in the next few slides are ALPS 1, 2, and 3. So I'm going to start by showing you how typical these galaxies are via the main sequence. So that's the relationship between the star formation rate and stellar mass of galaxies. So here I'm showing you the best fit main sequences at different redshifts from the Schreiber 2015 study. And now on the right-hand panel, I'm showing you the rest frame optical half-light radii as a function of the offset from the main sequence. And I've quantified this as the specific star formation rate of the galaxies relative to the specific star formation rate of a galaxy on the main sequence at the same redshift. So these gray points in the background here, these are all the galaxies between redshift 1 and 3 detected in the Hubble Ultra Deep Field. Red squares are all the aspects sources for which we have 1 millimeter observations. And these red stars are the 3 galaxies I'm talking about today. So you can see that these 3 galaxies are fairly typical and that they lie on or at most a factor of a few below the main sequence. So they're not outrageous starbursts, for example. So to compare the extent of the stars, dust, and molecular gas, we analyzed the 1.6 micron HST imaging and used ALMA observations at 1 and 3 millimeter. So these ALMA observations included both the Aspects Large Program data, data from paper by Dunlop in 2017, and a targeted follow-up program observing the CO emission. So to quantify the spatial extent of each kind of emission, I fit 2-dimensional disk models, both in the image plane and for the ALMA data directly in the visibility plane. So these models are parameterized by some inclination, a position angle, and a half-light radius, which is what we're trying to quantify. And I'll spare you all the annoying details of this fitting. Okay, so let's take a look at how these three extended galaxies compare to the high redshift galaxies that have been observed so far. So I'm going to start with my favorite galaxy, ALPS 2. It's my favorite because it's quite the outlier. So the dust in this galaxy appears to be at least as extended as the CO and the stellar emission. So you can see this also in this little cutout at the top. And maybe I should also caution that the dust is at low signal to noise here at these large radii. But for the first galaxy, so ALPS 1, it seems to be more consistent with submillimeter galaxies that have been observed so far. So the dust emission is about twice as compact as the stellar emission and also more compact than the CO emission. I think the contrast between this galaxy and the previous one is particularly interesting because they have the same rest frame optical sizes, same star formation rates and stellar masses, and yet in this one, the dust emission is much more compact than in the previous source. Okay, and finally, for our highest redshift galaxy, both the dust and the CO emission are very compact. So although there seems to be some sort of extended spiral structure apparent from the HST imaging, we don't see this in either the dust or the CO emission. All right, so let's take a look at what we're actually probing with these sizes and what it implies if some galaxies have larger dust or CO extents. So what our measurements and those of previous ALMA studies are sensitive to are these very high gas density regions typical of nuclear starbursts. But our observations are barely sensitive to the densest spiral structure that's observed for local galaxies. So as an example, what I've done here is taken the long wavelength continuum observations of the local nuclear starburst NGC 253. I redshifted this and created mock observations with the same noise level and resolution as the 1 millimeter data for ALPS 3. So you can see that our observations wouldn't have picked up any spiral structure here, but would just trace the nuclear starburst region. So the fact that we measure such compact sizes for this galaxy and also for submillimeter galaxies is likely because of the high star formation rate and dust content in the galaxy centers. And for this, I also want to highlight some recent simulation-based studies, including the work of Rachel Cochrane, who's here at the CfA. So what these studies are showing is that this compact dust emission really traces the heating by star formation. And actually the dust emission is more compact than the dust mass distribution. So I would like to show you another example just so you get a feel for what we're probing with this data. So for this, I've taken the CO2 to 1 emission of the local galaxy NGC 3627. So this doesn't host a nuclear starburst. And we measure a similar maximum extent of the CO emission for our second galaxy as for this local galaxy. So supposing that this local galaxy has the same high molecular gas mass as our high redshift galaxy, and under the same observing conditions, we would have seen it like this. So you can see there's no way to discern any structure here. And actually what is interesting is that this galaxy would have appeared more compact than ALPS 2. Okay, so I'm going to make a not particularly smooth segue from these 2D comparisons because I want to talk a little bit about the motion of the gas and what this implies for the 3D structure. So using the CO data, we could also model the kinematics. So we measured the maximum rotation velocities and velocity dispersion of the gas. So here's just an example of the CO data, again, for my favorite galaxy. So the top shows you the velocity integrated CO line intensity. The middle is the intensity weighted line of sight velocity. And in the bottom is the intensity weighted dispersion. So to fit this data, we assume that each galaxy can be modeled by a thin rotating disk, again with some inclination to us. So here you can see the model, again in 2D, and the model that's been convolved to the same resolution as the data. And here's just the residual of this fit. Okay, so using this kind of fitting, let's take a look first at the velocity dispersions that we measured. So what I'm showing here are the velocity dispersions of our 3 galaxies, again, the red stars, compared to other galaxy samples observed so far. Just one thing to highlight though, this is really important, that all of these galaxy samples that I'm comparing to, they've all been observed in ionized gas. Now, another thing I want to point out is that these measurements, so our velocity dispersion measurements, and actually most of the other ones too, they're really upper limits. So these measurements include dispersions due to motion along the line of sight, as well as the intrinsic gas velocity dispersion. Okay, but still, I just want to point out that these measurements that we have here are roughly consistent with previous studies and with simulations. But what is very different is the rotation velocities that we measure. So we measure maximum rotation velocities of around 300 kilometers a second for these three galaxies. So this is like the Milky Way rotation velocity. And in this panel, I'm showing you the ratio of the rotation to random motion. So that's the maximum rotation velocity divided by the velocity dispersion as a function of redshift. You can see that our three galaxies are rotation dominated, which is similar to local galaxies, but very different to most of the high redshift galaxies that have been observed to date. Okay, so this might be a selection effect since we selected large and inclined galaxies, which are more likely to be thin disks, but it's also possible that the gas tracer here plays a role. So maybe this cold gas that we're probing has settled into a thinner disk than the ionized gas. I think we really can't tell yet with the data at hand. Okay, so I need to come to my conclusions now. So first of all, we found that the molecular gas masses inferred from single band dust continuum observations are consistent with what we measure from CO1 to 0 for massive star-forming galaxies at high redshift. So this implies that the dust emission traces the bulk of the molecular gas. But dust emission is not a straightforward tracer of molecular gas at large radii. So in our work, we compared the extended dust and CO emission of three galaxies at redshift 2. And for the first time, we observed a main sequence galaxy where there appears to be a really significant component of dust and molecular gas at large radii. But we also find evidence for a population of high redshift galaxies where the vast majority of this dust and molecular gas is within a compact nuclear starburst region. And in contrast to most high redshift galaxies, we find that the gas motion for these three sources is rotation dominated. So I'll leave it there because I've probably led to more questions than I've answered with the talk. So I'm happy to take any more questions that come up.
Okay, so we have a question. Anthony, start, please.
Hi, yes. So this is not a criticism of your talk so much as a criticism of the whole field, and it's a criticism that I've been making for decades, which is that early on in this field there was a tendency to conflate observational quantities with theoretical quantities, and in particular the mass of molecular material with the observed brightness of the CO line. And you know, this has been a fight back and forth among various groups, and I think the way forward is to stick to the observers should stick to observables, and then if you want to understand those observables, you have to go to models and then see if your models can reproduce what is actually observed. And it's not productive to say, you know, I've measured CO and therefore I definitely know what the mass of this galaxy is. I mean, there certainly are clear examples where that is in error by, you know, factors of many. So
I totally agree. So one thing that I really skipped over here is that there is a second pair of axes, which are almost, I mean, in this case, not quite the observables. So really what I have measured here is a CO line luminosity and a dust continuum luminosity, which also correlate well. But yeah, point taken.
Okay, I'll get off my high horse there.
Alisa Goodman, please.
Hang on. Yes, now I have to remember my question. Oh, yes. When you were showing the rotation velocities and the velocity dispersions, if you could go back to that plot. Yeah, you mentioned that the high dispersions in the plot on the left might have some contribution from the rotation itself. I think you sort of said that in passing, but I didn't get whether you tried to subtract that or model like what the inclination would have to be to account for that.
So it's not so much the rotation, but for example, motions due to warps or motion inside a thick disk. So this is motion that isn't the intrinsic velocity dispersion, but that can easily be confused with it. So no, we didn't try, because with the resolution of our data, that's pretty much impossible to model.
Right, but would a simulation give you any idea what?
Yes, yes, it's something that I really want to do in the next 2 years.
I got it. Okay, well, I'm curious. Thank you.
Okay, so the last question is for, I'm sorry, the name says Clara, C-O-A-D-A. Is there?
Yeah, I have a question about, again, about the velocity dispersions. How do you measure them? Are the sources unresolved, so you just take a single line and measure?
So they are resolved. So what we do is, maybe if I go back, this isn't the best plot, but we use a Python package called CubeFit. So what this does is model the emission in 3D. So it is resolved, but you can see here that if we collapse it, we have like a few resolution elements per galaxy. And we have around 50 kilometers a second channels. So what we have is a model in 3D where you can see this disk changing as a CO line would. And we do an MCMC analysis on this. So I don't know if
I'm just trying to understand the data that went into this. So is this a moment analysis of the line, or?
No, I'm only showing you the moment analysis of the line, but what we use is the full 3D data cube.
Okay.
Yeah.
And so the dispersion is like the average over all the pixels?
No, it's actually the dispersion of the model itself. So I'm not measuring this directly here. I'm supplying it some model which has a rotation velocity and a dispersion. And I'm saying which of these models that I'm fitting to the data fits best via some chi-squared analysis.
Okay, thanks.
Yeah. Okay, let's thanks again our speaker. Thank you, Melanie, so nice of you. Can you use your clap emoji so we can say properly, thank you so much. And if you would like to continue talking with our speaker, please, you can still sign up in her schedule today. She's from Europe, so please take in consideration that she's only able to be with you before 1 p.m. And this leads us to our second speaker now. Thank you so much, everybody. Oh, let me. Okay.
Okay, thanks, Tatiana. The second speaker today is Jamie Law-Smith. He's a grad student at UC Santa Cruz working in high energy astrophysics. So he's also done some work in theoretical physics. He has worked on tidal disruption events, binary neutron stars, host galaxies, and AGN accretion disks. He's also worked on de Sitter space and string theory. So feel free to ask him about that during the question. He did his undergrad at Harvard, so it's a pleasure to have him back. And Jamie, go ahead.
Thanks, Griffin. I'm just going to share screen. Oh, it says host disabled screen sharing.
That shouldn't be the case, but let me see if I can fix that.
That didn't happen earlier. I'll keep trying.
I did co-host, and then when you left, I forgot.
Oh, right.
Okay, now it's working. Now it's working. Okay, is this working?
Yep.
Great. So hi, I'm Jamie Law-Smith, and I'm a graduate student at UC Santa Cruz. And today I'm going to talk about interactions between stars, black holes, neutron stars, and the galaxy. So let's start by just thinking about stellar interactions in the galaxy at large. So this is the cartoon of the different sites for stellar interactions in the galaxy. And in the center of most galaxies is a supermassive black hole and a nuclear star cluster, and perhaps an actively accreting disk or the faint remnants of a disk. And here, for example, a star can be tidally disrupted by the supermassive black hole, or binary star encounters with the supermassive black hole can lead to hypervelocity stars. And there may also be interactions between stars and the disk. So in globular clusters, there's also a high stellar density, and so interactions between stars are more likely. And just as an example, you can have stellar mergers, which are thought to produce the blue stragglers on the HR diagram. And some globular clusters may also host intermediate black holes, which, if they exist, are a key missing link between stellar mass black holes and supermassive black holes. And in addition to each of these sites, the field can also host binary star systems. And binary star systems, of course, can lead to, for example, supernovae, gamma ray bursts, compact object binaries that produce gravitational waves. So my goal is to use these interactions as tools to better understand black holes at all masses, how stars live and die, and the dynamical mechanisms operating in galaxies. So in particular, I'll focus first on interactions between a star and a supermassive black hole in the form of tidal disruptions of stars by supermassive black holes. And I'll spend most of my time here. Second, on interactions between two stars, and in particular, binary neutron star formation. And third, on connecting these systems to their galactic birthplaces. So first, zooming into the galactic center, tidal disruptions of stars by supermassive black holes. So a tidal disruption happens when a chance encounter with another star knocks a star onto an orbit that brings it close enough to the central supermassive black hole such that the tidal force across it overcomes its self-gravity. And at this point, this leads to the definition of the tidal radius, which depends on the mass of the black hole and the structure of the star. We also have the definition of beta, which is the impact parameter, which is the ratio of the tidal radius to the pericenter distance. So higher beta is closer to the black hole. And in a tidal disruption, the passage time through pericenter is roughly the dynamical time of the star, which is a nice fact. And roughly half of the debris in a typical disruption is unbound, and half remains bound to the black hole or becomes bound to the black hole. And there's often a surviving remnant. And it's this bound debris that falls back towards the black hole, and the rate of return of the bound material to the black hole, or the mass fallback rate, directly informs the light that we see in a tidal disruption event. So when a tidal disruption happens, we see a rapid increase in brightness, followed by a slower decay that coincides with the nucleus of the galaxy. And through a detailed theoretical understanding of tidal disruption itself, coupled with comparison to well-sampled observations, we can learn about the properties of the disruption. So what was involved in the disruption, the black hole mass and spin, the stellar mass and age, and also things like accretion physics on timescales of weeks rather than the much slower evolution of AGN disks. And through the relative rates and demographics of tidal disruptions, we can learn about galaxy properties, such as the dynamical mechanisms operating in galactic centers. And we're currently in the midst of a data explosion in TDEs. So there's well-sampled photometry and spectroscopy for dozens of TDEs. And we expect thousands of TDEs with the Rare Rubin Observatory. So here I'm just showing some examples of exciting observations in the past few years. So we have photometry that captures the early rise, peak, and decay of these transients. There's spectra that show hydrogen and helium features, as well as metal lines such as carbon and nitrogen. And in the context of this talk, one gets a very good fit to the optical UV light curves. Some examples are shown here by directly using the results from our simulations, which I'll show. And in particular, the result of that mass fallback rate. So the mass return to pericenter of the debris from the disrupted star. So on the left, I'm showing fits to light curves. And from these fits, we're able to constrain, importantly, the black hole mass and many other properties of the disruption, such as the impact parameter, the efficiency of accretion, and many other important things. So on the right, I'm showing fits to several of these properties for a few TDEs. So with the aim of extracting all of these physical parameters from events, we developed this stars library. So stellar TDEs with abundances and realistic structures, the stars library. So our framework is to build stars in MESA, which is a 1D stellar evolution code. and to calculate their disruption in FLASH, which is a 3D adaptive mesh Eulerian hydrodynamics code. And so we get accurate stellar structures. We're tracking the composition of the gas for an arbitrary number of elements, and we're using a Helmholtz equation of state, which is the backbone of the MESA equation of state. So we study the whole parameter space of main sequence stellar structures and impact parameters, or distance to the black hole, from grazing encounters to full disruptions. And our results, which I'll show a few examples of, so we provide the mass fallback rate to the black hole, composition of the fallback material, and several important derived quantities. And importantly, as a new thing, we interpolate all of our simulation results and the time evolution of these simulation results so that you can request the mass fallback rate for any stellar mass, stellar age, and distance to the black hole using a GitHub tool. So here's a visualization of one of our simulations. So on the top right is the orbit of the star as it passes through pericenter. And in this visualization, we're in the frame of the star and zoomed in on the star as we pass pericenter. So you can see tidal tails coming from the star, but here we're just focusing on the surviving remnant. As in this case, there is a surviving remnant following the disruption. And here's an example of the tidal tails and the stratified density structure of the debris following a tidal disruption. And again, one of these tidal tails remains bound to the black hole, and it's from this that the luminosity of TDEs is generated. And I just want to point out here that the stellar structure is imprinted on the spread in binding energy of the debris, which in turn determines the mass fallback rate to the black hole. So the stellar structure is imprinted on the mass fallback rate to the black hole, which I told you it can be directly related to the luminosity evolution of TDEs. So here are some results from our simulations. So these are mass fallback rates to the black hole. And each panel is a different stellar mass and stellar age. And the different lines are different impact parameters or distances to the black hole. So we interpolate all of these curves in each of these three dimensions. So stellar mass, stellar age, and distance to the black hole, so that you can again obtain and request the fallback rate for any star and distance to the black hole. And I found that all of our simulations can be reduced to a single relationship or collapsed to a single relationship that depends only on stellar structure. So characterized by this single parameter, alpha in the top right, which is rho c over rho bar. So that's the ratio of the central density to the average density of the star. And it's a very good parameterization of the density profile of the star. So I'll just name, so this collapse happens with this scaled x-axis for these different quantities. And I'll just name the different key TDE quantities that I'm showing here without going into too much detail. So on the top left is the critical impact parameter for full disruption. On the top right is the mass lost or unbound from the star. So going from grazing encounters to full disruptions. On the bottom left is the asymptotic power law decay index of the mass fallback rate curve, which is observed in the late time luminosity evolution of TDEs. And the bottom right is the peak mass fallback rate. So this is related to the peak luminosity of TDEs. So another important concept, or sorry, component of these simulations is that we have the composition of the gas. So on the left-hand side, I'm showing 2D slices of the mass fractions of helium and carbon for a 1 solar mass terminal age main sequence star. So helium's across the top, carbon's across the bottom, and at 2 times. On the left is at the beginning of the simulation. On the right is a little bit after pericenter. And you can see the helium enhancement and the carbon depletion in the star's core are spread into the tidal tails. And so these compositional anomalies in the hydrodynamics are mapped via the hydrodynamics to the composition of the fallback material as a function of time. So that's shown on the right. So the x-axis here is time relative to the peak of the mass fallback rate curve. So when the event is brightest. So excitingly, we find compositional anomalies in the fallback material that appear before or at the time of peak fallback rate, so when the event is brightest. In this case, there's nitrogen and helium, which are enhanced before or at the peak, and carbon is depleted before or at the peak. So, but how does this material actually turn into light? So this is a very active, unsolved problem in TDEs and very important, obviously. So this is some work we're doing in this direction. So this is a simulation of TDE disk formation. So the star passes pericenter here, and then we'll focus a little bit on the expanding tidal tails, and half of this debris is roughly unbound. And again, this is for the same star for a 1 solar mass terminal age main sequence star for a full disruption. So the dissipation here is from the shock 1, or the nozzle shock at pericenter. And excitingly, so this is a density rendering, but we have the disk chemical structure of this evolving disk and expanding debris bubble. So this is a key step in connecting the actual hydrodynamics of the encounter to the observed spectral lines and in understanding the spectra of these events. So as I said, this was density, and here's a visualization of the chemical structure of the TDE disk. So this is at a particular time for that simulation, going from left to right, just zooming in a bit more. And in white is hydrogen, red's helium, blue's carbon, and green is nitrogen. So the story here is that we have a very stratified and distinct density structure. So it'll be really exciting to import this into radiative transfer calculations and actually start to make predictive models for the spectra of TDEs, and actually start using them to extract quantities, physical quantities. Okay, so we've talked about interactions between a star and a supermassive black hole at the galactic center. Now let's switch gears to discussing an interaction with a physical scale much smaller than that between a star and a supermassive black hole. And that is interactions between two stars, and in particular, the common envelope phase and binary neutron star formation. So the common envelope phase of stellar evolution, just a quick outline, is when two stars share an envelope. And it can shorten the orbital period so that the resulting compact objects merge in a Hubble time. This is why it's so important. So if the envelope is not ejected, this leads to a stellar merger. So that's on the bottom right of this cartoon. And if the envelope is ejected, this can lead to a compact binary that merges via gravitational waves. So that's on the bottom left. And we're going to discuss binary neutron star formation via common envelope ejection in 3D hydrodynamics. So our system is a 12 solar mass red giant, which will evolve after a simulation to a neutron star, and a 1.4 solar mass neutron star. So this is the evolutionary history of the red giant star, radius as a function of time. And we use a 1D formalism, which is adjusted from the alpha energy formalism in common envelope studies to predict the radii at which common envelope ejection is possible. So that's these shaded regions. And the red circles are stars that we simulate. So in the bottom panel, zooming in, there's a bit more detail in these plots than we're going to get into. But at each age, the 1D formalism predicts the radius range inside the star in which common envelope ejection is possible. So these are the colored shaded regions. And we excise the part of the envelope with negligible binding energy, so less than 0.1% of the total binding energy of the star. And we start the neutron star close to these radius ranges where we think common envelope ejection is possible. And we used a 3D study of the common envelope drag coefficients and a 2D integrator to determine the initial velocity of the initial velocity vector of the neutron star. We also compared to a circular initial velocity vector. And looking ahead a little bit, the red X's are where the envelope is ejected in our 3D hydrodynamic simulations. So the predicted ejection ranges are consistent. So here I'm showing gas density for the red giant, and the neutron star will be initialized on the right. And the different shells here are different density isosurfaces of the red giant. And as you can see, as the neutron star orbits, you can see it disrupting the outer shells of the star and sweeping and clearing out material. So in these simulations, we fully resolve the core of the star to less than 0.005 our sun. And I think this framework's really exciting because it can be used to simulate virtually any binary star system, especially if we extend it to initialize 2 stars on the grid. So we can simulate a wide variety of interactions between stars, from stellar mergers to common envelope episodes leading to gravitational wave sources. And these are the first simulations of common envelope ejection leading to a binary neutron star in 3D hydrodynamics. So here I'll show one picture of this common envelope ejection. So this is a sum of the kinetic and potential energy, where the pink purple is bound, so energy is less than 0, and the yellow is unbound, so energy is greater than 0. And there's that blue isosurface at E equals to 0. So at early times, the energy of the entire star was negative, of course, but at late times, the envelope is unbound.
5 minutes.
Thanks. Okay, so here I'm showing the trajectory and orbital separation for 2 models. So the red and the black are actually the same star, but with 2 different initial velocity vectors. So circular, and that informed by the integrator that I explained briefly. So on the left is just the trajectory of the neutron star as it orbits the center of mass of the red giant. And the right-hand side is the orbital separation as a function of time. So all of our simulations give qualitatively similar results to this. And we find final orbital separations of roughly 1 to 3 solar radii, leading to binary neutron stars that will merge within 0.01 to 1 gigayears. So this is the binding energy of the envelope as a function of time for all of the models we study, including a line from a numerical convergence study. And as you can see, we find envelope ejection for all of our models as the binding energy transitions from E less than 0 to E greater than 0 unbound. So this is the composition of the debris for hydrogen in the top row, helium in the middle row, and nitrogen in the bottom row. And having this kind of chemical abundance information is exciting for several reasons and for future research in binary star end fates, but I'll just note here that the hydrogen envelope is completely ejected, leaving no hydrogen on the Swift star. Okay, so we've talked about interactions between stars and supermassive black holes and between 2 stars. And now let's zoom out between these roughly AU scale phenomena to the kiloparsec scale to discuss how these events are connected to their galactic birthplaces. Okay, so I conducted this systematic study of TDE host galaxies in the context of galaxies in the local universe. And I'll just highlight some of the results here. So on the left-hand side, and this was not discovered by me, but is important, is that TDE host galaxies appear to be unique. So they're overrepresented in these rare quiescent Balmer-Strong, or E+A galaxies, where there's little ongoing star formation in the y-axis there, but there are young stars. It's on the x-axis. And in a more direct galaxy evolution context, on the right-hand side, we found that TDE hosts appear to live in this transition region in galaxy formation. So the green valley between star-forming spiral-like galaxies and quiescent elliptical. So the star-forming mate sequence is the blue line with degrees of quiescence below it there. Another exciting finding is that we found that TDE host galaxies have more centrally concentrated light profiles for their black hole masses, irrespective of E+A classification. This is on the left-hand side. You can see this with galaxy Sirsic index, which is just a parameterization of the central light concentration of the galaxy. So higher Sirsic index is more centrally concentrated. And on the right-hand side, this is evident visually. So for just 2 TDEs examples on the top panels, TDE host galaxies, we show a random SDSS galaxy on the bottom panels, matched on redshift, stellar mass, but with the median Sirsic index of galaxies at that stellar mass. So this higher central concentration is a physical explanation of why TDEs occur in these galaxies. So there's higher stellar densities, higher rate of 2-body interactions, and thus a higher TDE rate. Now let's mention that this galaxy matching framework is general and can be applied to any type of galaxy. So we've recently also applied it to changing look AGN. So an intermediate scale between the central supermassive black hole and the galaxy as a whole is a central accretion disk, if it's present. And one would generically expect accretion disks to have embedded stars. So I'll just introduce this model I've been building with Doug Lin on the structure of AGN disks with embedded stars. So we account for energy and momentum feedback from stars, supernovae, and stellar remnants. And we find that the structure in the outer regions of these disks is actually dominated by these sources. And there's a self-regulated star formation. So if you form too many stars, you blow off the disk, and then you form fewer stars, allowing gas to recollapse and then form more stars again. Now I'll just leave you with my summary. So of the different interactions I've talked about on the left, and the broad scientific goals of these studies in blue on the right. I think I'm out of time, so I'll stop there. Thanks.
Great, thanks, Jamie. Let's give him a round of applause here. Do we have any questions? If you have any questions, just raise your hand. Yvette, go ahead.
Hi, so really nice talk. I'm working a bit on the radio evolution of TDEs and things like that. And then of course in radio, we can also track the density of that inner bit of the galaxy. So I was very interested when you said the light profile in your fairly recent slide, how it's more concentrated at the center. And I was wondering if you've thought then how that relates to the density information we have for, you know, the 10-ish max radio TDEs that we have.
So at what scale is that density information? Like physical?
So that's like very close still, because most TDEs are, you know, they just haven't had physical time to it. So let's say inner parsec or something.
Yeah, so that's the really key kind of inference or like, you know, extrapolation we're making, because these are really kiloparsec scale properties, these global galaxy properties. But somehow the local, you know, inner parsec knows about these global galaxy properties. So it seems that the story here is that you have higher stellar densities. And so, as I said, those lead to higher TDE rates. But yeah, the X-rays are a little bit tricky to think about. I'd be happy to talk to you more about that later.
Yeah, I'm signed up to talk to you this afternoon, so we can.
Oh, great. Awesome. Great.
Any other questions? I actually have a question myself. If we go back to the beginning of your talk, I was interested to see that you had written down some like basically analytic scaling relations for TDEs, where you can just extract the properties based on, what did you say? That there was a critical density or something like that?
Yeah.
Does this imply that like you could just write down an equation and you know simply like convert this to observable so that you could actually measure these properties from observed TDEs or something like that?
Yeah, I mean, I think, you know, we haven't done any of this work, but I think this is kind of exciting to think about because, and I also think that because there's that sharp 1/3 factor, which comes up in TDE theory, I think you could probably derive this from TDE theory. And in principle, you don't have to run any more simulations because I didn't show this, but I think we can scale all of our simulations to basically any stellar structure. So I think you could, at least for these key quantities, and one day I have a dream of deriving the light curve analytically for all TDEs, but you could go directly from an observation just to plug in a few numbers and then you get these physical quantities.
Yeah, that dream is exactly the dream that I was imagining also. That would be really cool.
Awesome.
And yeah, it's also, you bring up a good point that like, I wonder if you could just derive this from theory then, if it's really so clear, which it seems to be from all these plots. So that is really cool.
I think it can be done. I just haven't tried yet.
Do we have any other questions? Okay, if not, I think we're almost at the hour. So let's thank both the speakers again. Jamie also still has some spots left on his schedule this afternoon, so feel free to sign up to talk to him. Thanks everyone for coming.
Thanks.
Hey, Jamie.